Hey guys, so today we're going to be covering topics from your Math 200 class for Chapter 7, which goes through the normal probability distribution. So we're going to start with Section 7.1, which just talks about the properties of the normal distribution, but we're going to talk about what a probability density function is first, and we're going to take a look at one other small distribution to kind of illustrate this concept. So a probability density function is an equation. It's used to compute probabilities of continuous random variables, and it has to satisfy two different properties. The first is that the total area under the graph of the equation over all possible values for the random variable has to equal 1, and this is kind of a continuation of us knowing that when we sum all of our probabilities together, we get a value of 1. And then the height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. So this again goes with our probability kind of rules that we had back from Chapter 5 and Chapter 6, which told us that we can never have a negative probability. So the first distribution we're going to look at is the uniform distribution, and we're just going to spend a couple of slides going through this. This was first introduced way back in the beginning of the semester. I don't remember if it was Chapter 2 or Chapter 3. But they showed you a couple of different distributions, and the uniform distribution was one of them. So let's look at an example here. So let's suppose that UPS is going to deliver a package to your front door, and you know that the arrival time is going to be somewhere between 10 and 11 a.m. So we're going to let the random variable x represent the time from 10 a.m. when the delivery was supposed to take place, meaning that the delivery could be at 10 a.m., which would mean that x would be equal to 0. It could be at 11 a.m., which would mean that x is equal to 60, because that's 60 minutes. And we're using 1-minute intervals of time between x equals 0 and x equals 60, and we're saying that they're all equally likely, meaning that we have basically the same chance of our package arriving between 10:15 and 10:16, between 10:40 and 10:41, between 10:50 and 10:51, and so on. So the random variable x can be any value in the interval from 0 to 60. So we can write it like this: 0 is less than or equal to x, which is less than or equal to 60, because any two intervals of equal length between 0 and 60 are equally likely. The random variable is said to follow a uniform probability distribution. So if we take a look over here, this is what the uniform density function actually looks like, or our uniform probability distribution. And it really just illustrates the properties for the previous example. So if you look, we're going to have x equals 0 over here. We have x equals 60 over here. Our random variable in this case is time. It's the number of minutes that it takes for our package to arrive after 10 a.m. And you can see that this is just shaded solidly because it could take on any value between 0 and 60. Now, we know that in order to find the area of a rectangle in general, we take length times width. So the length of our rectangle is 60, okay? Or we could call this the width, I guess. So the width of our rectangle is 60. So we know that the height, or the length we could call it, has to be 1 over 60, because of the fact that we know that the area under a probability density function has to be equal to 1. So when we multiply 1 over 60 times 60, we get a value of 1. So values of the random variable x less than 0 or greater than 60 are impossible. So if we take a look at those values on our little graph here, you'll notice that this part is not shaded, okay? The probability of this happening is just 0. The probability of getting a value greater than 60 is also 0. So there's no shading there. Now, the area under the graph of the density function over an interval represents the probability of observing some value in that interval. So for example, if we want to find the probability of choosing a time that's somewhere between 15 and 30 minutes after the hour, what we're going to do is we're going to take the grouping of our uniform density function from 15 to 30 minutes, and we can just kind of shade this here. So we have 15 to 30 minutes. We know that this is now a rectangle that has a width of 15, okay? And then the height of this rectangle is still 1 over 60. So in order to find this area, all we have to do is take 15, which is our width here, and multiply by the height of 1 over 60, and we get 0.25, which means that basically we have a 25% chance of our UPS delivery happening between 10:15 and 10:30 if all times between 10 and 11 are equally likely. Now, relative frequency histograms that are symmetric and bell-shaped are said to have the shape of a normal curve. And we talked about this the same time that we talked about the uniform density function. It's just a different type of probability distribution, and it's one that we're going to take kind of a closer look at. So if a continuous random variable is normally distributed or has a normal probability distribution, then a relative frequency histogram of the random variable has the shape of a normal curve, meaning that it's bell-shaped and symmetric. So looks kind of like a bell here, and if we draw a line down the middle, it's symmetric on both sides. We could flip it over the left or the right, and it's completely symmetric. Now, there are two inflection points. You don't have to worry about these too much, but inflection points are when the concavity of your graph changes. So when it goes from concave up to concave down. And this happens at mu minus sigma and mu plus sigma. Now again, mu is your mean. This is from a previous chapter. Sigma is your standard deviation. So if we take a look at what some different examples can look like with different means and different standard deviations, we can see how these graphs kind of differ. So this top graph shows something where we have the same standard deviation. The pink and the blue both have a standard deviation of 1, but they have different means. The pink graph has a mean of 0, so it's centered around the value of 0. The blue graph has a mean of 3, so it's centered around a value of 3. So you can see that the blue graph is just a shifted version of the pink graph. Now down here, we have different standard deviations. So if you look at the pink graph, it still has a mean of 0, still has a standard deviation of 1, which is a fairly small standard deviation, okay, in comparison with this down here where we have a standard deviation of 2. So the smaller the standard deviation, the more grouped together my data. So you'll notice for the pink graph, I don't have as much spread in my data. Everything is kind of grouped in the middle. But with this blue graph, I have a larger standard deviation. So even though the means are the same for the pink and the blue graphs down here, the standard deviation for the blue graph is larger, so it's more spread out. So there are several properties of the normal density curve. You do not have to memorize all of these, but you need to be familiar with them and understand them. So the first is that it's symmetric around the mean. The second is that because the mean and the median and the mode are all the same, the curve has a single peak and the highest point is going to occur at x equals mu. There are two inflection points at mu minus sigma and mu, this should be plus sigma, sorry about that typo. The area under the curve is 1. The area to the right of mu is going to be the same as the area to the left of mu, both of which are going to just be 1/2. And as x increases, the graph is going to approach but never actually reach the horizontal axis. And as x decreases, the graph is going to again approach but never actually reach the horizontal axis. And then we also have the empirical rule, which is back from chapter 3 as well, which tells us that 68% of our observations when we're talking about the normal curve are within 1 standard deviation, 95% are within 2 standard deviations, and 99.7% are within 3 standard deviations. And these are approximations, okay, so you'll see the word approximately attached to each. It's important to note that these are not exact. The only way that we would get exact values would be using some kind of statistical software, and we still end up rounding our answers. So here's a visual representation of our empirical rule, which hopefully you're familiar with already. So you have your mean in the middle. We've added a standard deviation, added another standard deviation, added another standard deviation, and we've done the same with subtraction in this direction. And you'll see that they have labeled on here the 68%, the 95%, and the 99.7%. Now, as mentioned before, you can memorize either the 68, 95, 99.7, or you can remember these little values as well. Either way works. So when you're talking about area under a normal curve, let's just suppose that a random variable x is normally distributed with a mean of mu and a standard deviation of sigma. The area under the normal curve for any interval of values of the random variable x is going to represent, you can either refer to it as the proportion of a population with the characteristic described, or the probability that a randomly selected individual from a population will have the described characteristic. So let's look at a couple of ways that we can kind of form these interpretations. So this is just about understanding what the value that you actually get actually means. So let's take a look at an example here. The weights of giraffes are approximately normally distributed. The mean is 2,200 pounds and a standard deviation is 200 pounds. So we want to draw a normal curve and we want to go ahead and label our parameters. And then we want to shade the area under the normal curve to the left of 2,100 pounds. And let's just say that we know that the area under the 2,100 pounds is 0.3085. So we want to provide two interpretations that use this value of 0.3085. So if we take a look here, we have our normal distribution drawn, nice bell curve here, it's symmetric. 2,200 is in the middle, and we've labeled a standard deviation in each direction 3 times. And then 2,100 is going to be smack dab between 2,000 and 2,200, and we want it shaded to the left. So the way that we would interpret the value, which was given as 0.3085, is one of two things. We could either say that the proportion of giraffes whose weight is less than 2,100 pounds is 0.3085, or I could say that the probability that a randomly selected giraffe weighs less than 2,100 pounds is 0.3085. These two interpretations are one and the same, it just depends which one you like better. The other thing I want to point out is that you can always interpret these as percentages as well. There's nothing wrong with that. Okay, section 7.2 talks about applications of the normal distribution. So 7.1 was just getting you used to what the normal distribution is all about, what its properties are, and just a very basic introduction. Here we're actually going to be solving some problems. So we start with the formula for a z-score, which we have looked at before. So let's suppose that the random variable x is normally distributed with a mean of mu and a standard deviation of sigma. We know that the random variable z is calculated by taking our x minus mu and dividing by sigma. We know that it's going to be normally distributed, the mean is going to be 0, and the standard deviation is going to be 1. This is called our standard normal distribution, or standard normal curve. So the random variable z is said to have a standard normal distribution. So if you look here, here's kind of a graphical or representation basically of your standard normal curve, which has z values along the bottom. It has a mean of 0, standard deviation of 1. So the whole point of calculating a z-score is to be able to take a normal random variable that has a different mean and a different standard deviation and transform it into this standard normal curve. So the way that we used z-scores before is to compare, like you guys had a question that asked you to say, did the student do better on their geography test or their math test or whatever it was. And in order to figure out which test the student did better on, you had to standardize those scores to the same scale, which was the standard normal curve. So it allows you to compare things that you would not be able to normally compare. The other good example that I can think of off the top of my head would be comparing male heights with female heights. So typically males are much taller, but what we could do is we could take a male height and we could take a female height. We could standardize both of them and we could say which person is taller compared to their own gender. And the other nice thing about the standard normal curve and calculating a z-score is that it allows us to use table 5 in your book to actually look up probabilities, which is really important for this section. So there are 3 main types of questions that we're going to want to be able to answer. There are other small questions too, but these are kind of the 3 basic ones. The first is going to be if you're trying to find the area to the left. Okay, so in order to find the area to the left, really what you're doing is you're taking your normal curve and you're shading to the left. And in order to solve those types of problems, all you have to do is calculate a z-score and then look the value up on the table. I'm also going to show you guys how to do this in StatCrunch in a few slides. If you're trying to find the area to the right, you start the same way, you just shade to the right this time. You calculate a z-score, but then when you look the value up on the table, you have to subtract it from 1. So the whole idea with this table is that the table values give you the probability of selecting something that is to the left, okay? So the left is kind of your default. If you want something to the right, then you're going to have to take 1 minus your table value. And then the other type of problem is finding the area between two things. So that's kind of equally simple. Basically what you have to do is you have to calculate two different z-scores, look both values up on the table, and then you just subtract those values from one another such that you have a positive answer. So let's take a look at an example here. So IQ scores can be modeled by a normal distribution with a mean of 100 and a standard deviation of 15. And we would like to calculate the z-score for someone whose IQ score is 120. So in order to calculate a z-score, I always take whatever I'm interested in, which in this case is my 120. I subtract my mean, and then I divide by my standard deviation. And one thing you want to be sure of is that if you're doing this in your calculator all at once, you want to make sure you put parentheses around the numerator. So you should get a value of 1.33. So an individual whose IQ score is 120 corresponds to 1.33 standard deviations above the mean. Now, I'm going to pull up a table now, so let me kind of minimize out of this real quick. And what you're going to do is you're going to take Table 5, which is in the packet provided to you. It's also in your ebook, okay, if you don't have a physical copy of the book. So I'm going to go here. It looks something like this. And all we're going to do is we're going to look up 1.33. So in order to look up a value on the z-score table, all you do is you first look in the left-hand column and you find the first two digits that you're interested in. So I want 1.33, so I'm going to scroll down until I get to 1.3, okay, which is right here. And then these values along the top give you the hundredths place, okay, so it gives you the extra digit. So I want 1.33, so I go to 0.03 and 1.3, and I think I get 0.9082. Hopefully I'm looking in the right spot. Let's go back and see. Yes, 0.9082 should be this value, and it's shown in this picture here as well. So let me make this large again. So if I wanted the number of individuals or the proportion of individuals who have an IQ score of 120 or higher, basically, I know from looking up the value on my table that if I put a 120 here and I shade to the left, the area is going to be 0.9082. That's what my table gives me. It basically tells me that 90.82% of people score less than 120. But if I wanted the proportion of individuals who score higher, if you think about it, that's just using a complement rule, which tells us that we should take 100% or 1 and we should subtract the probability. And we just get a value of 0.0918, which would tell us that about 9.18% of test takers scored higher than 120. Okay, so here's an example here where they just they want you to just find the area, and this is not in the context of a question. So this one just asks us to find the area under the standard normal curve to the left of z equals negative 0.38. So I want you to pull out table 5 again, and I want you to see if you can find z equals negative 0.38. I'm going to give you a minute, and then I'll show you on the table here. Okay, so hopefully you found negative 0.3 here, and then you go over to 0.08, and you get 0.3520, which is the area to the left. So this one asked for the area to the left. Again, anytime you're finding area to the left, it's very simple. You calculate a z-score, in this case it's given, and then you look it up on the table. Now this one, I want the area under the standard normal curve to the right of z equals 1.25. So again, I want you to go to your table, look up z equals 1.25. I'll give you a second to do that, and then I'll pull it up. Okay, so if you look up 1.25, again, make sure, I didn't mention this, sorry, but make sure that you're paying attention to the signs here. So if we go down to 1.2 and then over to 0.05, I think it's around here, 0.89, to, let's see, 8.8944. I wasn't quite in the right spot. I was looking at 1.24. But if you look it up, you should get 0.8944 there. I would suggest using like a piece of paper to as kind of a straight edge for finding these. Now, 0.8944 gives you the area to the left. If you want the area to the right, then you have to take 100% or 1 and subtract this area that you found in your table. So anytime you're finding area to the right, you're going to do 1 minus your table value. So in this case, I take 1 minus 0.8944, and I get a value of 0.1056. All right, now we also have between type questions. So this one, I want to give you a minute, see if you can figure this one out. Between, what you're going to do is you're going to look up both z-scores first. So go ahead and take your table out, look up a z-score of negative 1.02 and look up a z-score of 2.94 and write both of those values down. Okay, so when you look up 2.94 on your table, you should get a value of 0.9984. So let me go there for a minute. So 2.94, I'm going to go to 2.9. Here's 0, 1, 2, 3, 4. So 0.9984. And when you look up negative 1.02, I go to negative 1.0 and then over to 0.02 and I get 0.1539. So if you recall from a few slides back, when we are worried about between type probabilities, all we do is we look up both values on the table and then we subtract the two in an order such that we get a positive answer. So you would never want a negative answer because you're not going to have a negative area. It just doesn't make sense. So in this case, you're going to take the 0.9984 minus the 0.1539, and you should get a probability of 0.8445. Okay, now this example is a little bit different, but let's take a look at this one. So the combined score on the GRE, combining both verbal and quantitative reasoning, is normally distributed. The mean is 1049 and the standard deviation is 189. And I want to know what the score of a student would be whose percentile rank is the 85th percentile. So this one's a little bit different because they don't give us a z-score. What they give you is the actual percentile. So what you need to do is you need to go to your table and you need to find the value of z that corresponds with the 85th percentile. So what you're actually going to do is you're going to go into your table and you're going to look in the body of your table this time and you're going to try to find a value that is close to 0.85. So let me give you a minute, it should be somewhere around here. So if you look, we have two values, 1.03 and 1.04. 1.04, the value of 0.8508, that's a little closer than the value of 0.8485. So 1.04 is the corresponding z-score. So essentially what we're going to do is we're going to still use our same old z-score formula, except in the place of z, I'm going to use the value of 1.04. And x, that's the thing that I'm interested in. I don't know what that is because I'm trying to figure out what the score is that corresponds with the 85th percentile. So step one is to look in the body of your actual table and find the z-score that corresponds with the desired percentile. Once you have that z-score, you just use your z-score formula, but this time you're solving for something different. So you plug in the mean, and you plug in the standard deviation. Those were both given on the previous slide. And then I'm assuming that you all know how to solve this type of an equation. All you have to do is multiply both sides by the denominator and then add the value of 1049. And you get a value, this is rounded, but a value when rounded to the nearest whole number that is 1,246. So that means that a score of 1,246 puts someone in the 85th percentile, meaning that they did better than 85% of test takers, and only 15% of test takers did better than that person, which is what I just said here. Person who scores 1246 on the GRE would rank in the 85th percentile. Okay, let's do one other example. This is kind of the hardest type of example in this section, but this is still one where we have to look up in the body of the table, but it's a little different. So it's known that the length of a certain steel rod is normally distributed with a mean of 100 centimeters and a standard deviation of 0.45 centimeters. And let's suppose that the manufacturer that we're working with wants to accept 95% of all the rods that are manufactured. So they only want to have to reject 5%. So what we want to do is we want to determine basically the acceptable lengths of the rods that are making up the middle 95% of those that are manufactured. So if you think about this one, if you have kind of just a plain old normal curve here, and we want the middle 95%, so this kind of tannish gray shaded area, that's 95%. So we know that I have to have 5% between these two blue tails. So between the two, since I have 5%, that means that I have 2.5% on the left and 2.5% on the right. So I need to find the values in my table that correspond with the 2.5%. The easiest way to do this is to just go back to my z table, and I'm going to look for 0.025, okay, or something very close to that. And what you'll find here is that at negative 1.6, I have a value that's exactly equal to 0.025. So I know that z equals negative 1.96 corresponds with an area of 0.025 to the left. Now, the other thing to keep in mind is that these distributions, when we're talking about normal distribution, it's symmetric. So if this is your first z value, your other z value is actually just going to be the positive version of this one. So it's going to be a positive 1.96. So now all I do is I use my normal old z-score calculation. Z equals whatever I'm interested in, that's my x, minus my mean divided by my standard deviation. I substitute my values in for my z, which I now know, my mean and my standard deviation, and I solve for x. And then I'm going to go ahead and give you a minute, make sure you get this one, and I also want you to work through this one over here, see if you guys can get a value for that. So if you worked through this side as well, you should get a value of 100.882. One thing that I want to point out is that these two values of x, if you average them, you should get the value of the mean, which was 100. They should be both the exact same distance from 100 because of the fact that our distribution is symmetric. So the length of steel rods that make up the middle 95% would have lengths between 99.118 centimeters and 100.882 centimeters. Now, at this point, you might have thought of the empirical rule. If you didn't, don't worry about it, but if that popped into your head, we know that the middle 95% is within 2 standard deviations these values of 1.96 are just slightly more exact. So when we learned the 2 standard deviation rule, we hadn't yet learned this. The actual value is 1.96. This is still a rounded value, but it's slightly more precise than the 2.0. Now, I want to take a look at how StatCrunch can be used for all of these calculations. So it's important that for your exam, you know how to calculate a z-score and look values up on the table. But it's also important that you know how to use StatCrunch for these, because once you're comfortable with using the table, there's no reason to not use the technology that's available to you. So let's look at the IQ example again. We know that IQ scores can be modeled by a normal distribution. Mean is 100, standard deviation is 15. And we're just going to go through these questions. So let me kind of minimize this a little bit. I'm going to scoot this off to the side and bring up my StatCrunch here. So what I'm going to do is I'm going to go into Stat, Calculators, Normal, and then all we really need to do is enter the information that you're interested in. So my mean is 100, so I'm going to type that in here, and my standard deviation is 15, so I'm going to type that in here. And this first one, I want the probability that I get a score that's higher than 120. So all I need to do is I need to change my inequality and change it to higher than 120 and click compute. So this proportion would be 0.0912. This is actually one we did earlier. About 9% of test takers are going to score higher than a 120. Less than 95 for B, I just change the direction of my sign. I type in 95. I can either click enter or compute, and I get 0.36944. So about 37% of test takers score less than a 95. Now, if you want between, all you have to do is go up here. Instead of selecting standards, you select between. The mean and the standard deviation still carry over from the previous, which is really nice. And I want between 112 and 131. I click compute, and I get 0.1925-ish. So about 19.25% are going to score between those two values. Now, if I go back to standard for a minute, if I want to know what test score corresponds to the 80th percentile, this is one of those kind of backwards ones where I had to look it up in the table. And you can actually use StatCrunch for this as well. It's pretty cool. You can delete this value because I don't know what it is. Leave it as less than, and then I want the 80th percentile, which means that I want the area to be 0.80 here. And now when I click compute, it actually fills in this value here for me. So that means that a test score of about 112, 113-ish corresponds to the 80th percentile. So what I would do at this point is I would go ahead and recommend that you pause the video and try all of the calculations that are on page 4 of your lecture notes for this week using StatCrunch, and make sure that you're able to replicate those answers. Now, the answers might be slightly different based on rounding, okay? But in general, they should be pretty close. So I would make sure that you can get all of those answers by hand and using StatCrunch. It would be a good time to go ahead and pause that and give that a try. All right, now we're going to take a look at section 7.3, which talks about assessing normality. So we know that in order to use a normal distribution, we have to have data that is normally distributed. So not all data, obviously, is normally distributed. A lot of things are not, but sometimes we think that something might be, but we want to test that. So we can use something called a normal probability plot, and what it does is it plots observed data versus what are called normal scores. Now, normal scores are just the expected z-scores of the data if the distribution is normally distributed. So expected z-scores of an observed value are going to depend on the number of observations that are in the data set. So if sample data is taken from a population that is normally distributed, a normal probability plot of the actual values versus the expected z-scores is going to be pretty linear. So let's look at this data here. We have Old Faithful geysers in California, and we want to know if there's reason to believe that the time between the eruptions is normally distributed. So we have 15 different eruptions here, time between them, and we want to know if it's normally distributed. So what we can do is we can look at this probability plot. A lot of times this is already going to be given to you. I'm also going to show you how to get something that looks pretty similar to this We can't make it look exactly like this in StatCrunch, but we can get pretty close. So if you take a look at this, the random variable time between eruptions doesn't look very normal. If you look here, we have kind of this outlier out here that's sort of sticking out. And then these data points look pretty close to the actual line, but this one it's really far away, okay? So it means that our data is probably not normally distributed. And in order to get this in StatCrunch, let me make this smaller for a minute, move this over, close out of this. I have my geyser eruption times. You go into graph, and then you do something called a Q plot. You select your geyser eruptions, and then you want to check this little box here, which has normal quantiles on y-axis. And like I mentioned, it's going to look a little bit different than the graph you see here, but you'll see the basic same shape. Okay, so you see this line here. You have all of these points that are pretty close to it, but then you have this one data item that is, it's really far off, okay? So that's the one that is out here as well, which is kind of just an indicator that it's probably not normally distributed. So let me make this larger again. That's really all you need to know from section 7.3 is to be able to look at a normal probability plot or create one in StatCrunch and answer the question of whether or not the data looks to be normally distributed. Now, section 7.4, this one's kind of a tricky one. And what it is it's the normal approximation to the binomial probability distribution. So, sounds a little confusing, not quite as confusing as it sounds, but I just want to go back and review the criteria for a binomial probability experiment. So this was back from chapter 6 from last week, and we know that an experiment is going to be binomial if the experiment is performed n independent times and it's a fixed number of trials. For each of the trials, there are two mutually exclusive outcomes, either success or failure, and then the probability of success is the same for each of the trials. So those are the things that need to be true in order to have a binomial experiment. Now, for some fixed probability, as the number of trials increases, the probability distribution becomes nearly symmetric and bell-shaped. So since we're using a continuous distribution to approximate a discrete distribution, so basically what we're doing is we're taking our binomial distribution, which is discrete, and we're going to use our normal distribution, which is continuous, in order to approximate it. So we have to use this correction for continuity, it's called, and we'll get to the kind of the rules in just a minute. But one thing that needs to be true is that in order to use the normal approximation for the binomial, n times p times 1 minus p has to be at least 10. And if that's the case, then the binomial random variable is approximately normally distributed. The mean is given by n times p, and the standard deviation is given by the square root of n times p times 1 minus p. Now I want to take a look at an example here. So we have some number of successes. We're going to look at this binomial histogram, sample size of 40, probability of 0.5. So 20 is smack dab in the middle because that's your n times p. So what we're doing is we're taking this binomial histogram, which are the blue and the green, just the shaded bars, and we're using this overlay of our normal distribution in order to approximate it. And if you compare the bar heights and this normal curve, they look really similar, right? And what you should notice is that there are some places where I have like a little bit of an extra bar sticking out here, or I have a little bit of a missing bar here. So this is where that correction for continuity comes in. So let's say, for example, that I want the probability that x is less than or equal to 18. If we think about that, if I take this probability and I want the probability that x is less than or equal to 18, and I were to use these binomial pieces here, what you'll notice is that I would be missing this little chunk here. That's not included under my normal curve. So in order to make up for that, what I do is I add a 0.5, that's my correction for continuity, to my value that I'm trying to find. So really, finding the probability that x is less than or equal to 18 is approximately equivalent to finding the probability that x is less than or equal to 18.5 on our normal distribution. Now, same kind of thing is true if I want the probability that x is just equal to 18. So that would be just for this kind of bar here. So in order to find this, I take the probability that x is between 17.5 and 18.5. Okay, so basically I'm overestimating a little here, underestimating a little here, but they kind of make up for one another. So in general, here are the list of corrections that need to be made. So if you're finding the probability of x being exactly one value, what you have to do is you have to subtract 0.5 and add 0.5, and then find the probability that x is between those two values. If you have a less than or equal to probability, you have to add 0.5. If you have a greater than or equal to probability, you have to subtract 0.5. And if you have a between probability, then you subtract 0.5 from the smaller value and add 0.5 from the larger value. Now, it's important that you understand kind of the idea behind this. So basically, we're using a continuous distribution, which is our normal distribution, in order to approximate our binomial. Now, the main reason for this kind of stemmed from something that happened in the past, which was that binomial calculations, before we had advanced technology, could be really, really tedious to do by hand, whereas dealing with the normal distribution was much nicer, okay? So what they did is they created this correction for continuity that allowed them to use the normal distribution to approximate the binomial. It's not as necessary as it used to be because of the fact that we can now use technology to calculate exact binomial probabilities that would have been really, really tedious by hand before. Now it's not so tedious, but this concept has kind of stuck around, and it's one of our course objectives, so we still cover it. But that's kind of the idea behind this and why we actually use it. So let's look at two examples here. So according to Experian Automotive, 35% of all car-owning households have 3 or more cars. This is a study we've referred to several times now. So in a random sample of 400 car-owning households, we want to know what the probability is that fewer than 150 have 3 or more cars. So this is going to be binomial. The sample size is really large, it's 400. So using our table, we don't really have a way of doing this. We could use StatCrunch or some other technology in order to calculate it, but we wouldn't be able to look it up just on our binomial table because the largest sample size we have is only 20. But first thing we want to do is we want to make sure that we would be able to use the normal distribution as an approximation. So in order to do that, we have to check that n times p times 1 minus p is at least 10. So our 400, which is our sample size, times our probability of success, which is 0.35, times 1 minus 0.35 gives us a value of 91, which is obviously larger than 10. So we're fine to use our normal approximation. So we need to find our mean, and that's found by taking n times p, this is from the previous chapter, 400 times 0.35, and you get a value of 140. You also need to calculate the standard deviation, which is the square root of 400 times 0.35 times 1 minus 0.35, again from the previous chapter, and you get a value of 9.54. So this is just the mean and the standard deviation of your binomial random variable back from chapter 6, section 2. Now, if I want the probability that I obtain fewer than 150 cars, fewer than 150 really implies that I would have 149 households or less. So the probability that x is less than 150 is actually probability that x is less than or equal to 149. So I want to scroll back real quick to this page here. And what you will notice is that all of the inequality symbols have equal to portions here. So this is less than or equal to, greater than or equal to, less than or equal to, less than or equal to. So whenever we're doing these problems, the very first thing we need to do after we've made sure that our assumptions are met and we've calculated our mean and we've calculated our standard deviation is that we need to make sure that we have a less than or equal to or a greater than or equal to symbol. This is a strictly less than symbol, so we need to fix that so that it's less than or equal to. So these two things are equivalent. Probability that x is less than 150 is really just the probability that x is less than or equal to 149, because we can't have like 149.7 households. Now I use my correction for continuity. If I have less than, then I add 0.5. And now what I'm going to do is I'm just going to use StatCrunch. So I go into the same place that I did before. This is still just a normal calculation. So I'm using the normal approximation, so I go to Stat Calculators Normal. I type in the mean that I found, which was 140, and I type in my standard deviation of 9.54, and then I want the probability that x is less than or equal to 149.5. That's using my correction for continuity, and I do compute, and I get 0.8403, which is the value that I have here. And let me scroll to the next one. We can take a look at this as well. We're going to use StatCrunch for this one too. Same type of setup. This one I want to know the probability that at least 160. So that would mean probability that x is greater than or equal to 160. Now, when you have greater than, the correction for continuity that you use is to subtract 0.5 from this value. So I get 159.5. I want at least, which means greater than or equal to. And I change 149.5 to 159.5. I have the same mean, the same standard deviation. I click compute, and it gives me a value approximately of 0.0205. So about a 2% chance. Now, we could also use our binomial calculator to calculate the exact value. Okay, so if we look here, for this one, for example, I have a sample size of 400. I have a probability of success of 0.35, and I want the probability of getting at least, so greater than or equal to 160 cars, and I click compute, and I get a value of 0.0212. This is an exact value. This value that we got here was using our normal approximation. So you can see that they're pretty close. They're not exact. Again, it's an approximation, so it's not going to be perfect. But before we had access to binomial calculators that did these kinds of computations, it was very, very tedious to do it by hand. So that's why the normal approximation exists. It's definitely the trickiest part of this chapter, so make sure you spend some time with it. Print off this here, which is in your lecture notes as well, so that you can kind of keep it by your side so you know which continuity correction to make. That's it, and please email me if you have any questions.